Hello, and welcome back, astronomy enthusiasts. This is the beginning of the lectures that would have been Tuesday, April 7th, week 3 of online instruction. I hope you and your loved ones are safe and healthy. I am doing well, as is my family, so things are going well. But we have lots of astronomy to cover, so let's get to it. I wanted to start by showing you a couple of astronomy pictures of the day. I am filming this on Monday. So this is Monday, April 6th, astronomy picture of the day. I'll share tomorrow's during office hours if you'd like to stop by. A beautiful picture of a galaxy. This is the NGC 1672, as you can see. And we're going to be learning about galaxies in the coming weeks. But this is a spiral galaxy. And particularly a barred spiral galaxy. What does that mean? It means that while there is a nice spiral arms that occupy the outer part of this galaxy, the inner part of this galaxy has a straight bar that goes straight across the center of the galaxy. And the spiral arms seem to emanate from the ends of that bar. We think, actually, the Milky Way is a barred spiral galaxy. I'm not sure that the bar is quite as pronounced as this, but interestingly, as we'll learn next week, we don't actually know. It's difficult to study the structure of the Milky Way galaxy. The last few of them are pretty cool too. If you're looking for some arts and crafts projects, Sunday's astronomy picture of the day was quite useful. It is a color the universe page. Print it out, color it. You can digitally color it if you want to. Interestingly, this a picture showing the universe that was done in the late 1800s. We haven't talked about the celestial sphere, but here's the celestial sphere with all the stars on it, and here is somebody peeking his head through the celestial sphere to see all the mechanisms that are going on, the hidden truths out there beyond the universe itself. So that's fun. The one before that is even better. I showed you last week, there was an astronomy picture today in one of the videos where it showed you that Venus was going to be passing right through the Pleiades. Well, here is a picture of Venus right in the Pleiades. There is the Pleiades star cluster. You might recognize it from class, although this is a much fainter view of it. You're only seeing the stars itself and not much of the nebulous. You can't really see any of the nebula around it. Here is the planet Venus right in it. So that's fun. If you've been out in the past few days, it's been clear, at least in Geneseo. You can see, or at least a few of the days, you could actually see Venus. Venus is so bright that it's actually hard to see the Pleiades right next to it. But if you look closely, you can see some brightish, at least a bright star or two that's pretty close to Venus. Venus has already moved past it now. If you go out tonight, Venus will be above the Pleiades, I believe. And you can look down and see just below it the Pleiades. So that's fun. Okay, let's get to today's review question, which is, what is the most massive element that you can create in the centers of stars via nuclear fusion? Is it, A, helium, B, carbon, C, iron, or D, uranium? You can pause the video if you want and look it up, or you can just wait for me to tell you what the answer is. We learned last time that the most massive element that can be created in the center of our stars via nuclear fusion is in fact iron. It is the end. Carbon is the end for the sun, but more massive stars in the sun will be able to burn carbon and subsequent elements. But nobody can burn heavier than iron, at least not in the centers of stars via nuclear fusion. The analogy we made last time was that an iron, sort of like nuclear fusion is kind of like squeezing the orange. And if you, the first squeeze of the orange you get a lot of juice out, and every subsequent squeeze after that, you get less and less juice out. By the time you get to iron, all of the juice has been squeezed out of the orange. There's nothing left. Iron is the most stable and lowest energy element, and therefore you cannot get any more energy out of fusing it with anything else. It is the end. Once you get to iron, eventually you will have core collapse and you'll have a supernova, and we talked about that last time. Great. So we're on to chapter 23 now. The deaths of stars. We talked about, we've gone through basically the entire evolution of a star now. We talked about ways that we know how stars work and measurements that we can make from stars. We talked about how stars are born. We talked about how stars age on the main sequence and off the main sequence. And chapter 23 is the last stellar chapter. It is what happens to stars as they die and what happens to stars after they die, what's left over. So let's get going with that. We've already talked about one of these end states, and that's a white dwarf star. It's not a star, it's a white dwarf. And we talked about how a 1 solar mass white dwarf is about the same size as the Earth. Interestingly, if you put more mass in this thing, it gets smaller. A 1.3 solar mass white dwarf is actually physically smaller than a 1 solar mass white dwarf. And these things are the end products of low mass stars like the sun. They are held up by electron degeneracy. But one of the weird properties of electron degeneracy is the more mass you put on there, the squishier it is, and actually, well, not squishy, but the more it squishes together, and the smaller it physically gets. So this thing obviously has more mass and less volume. It's way denser, or at least a little bit denser than this 1 solar mass white dwarf. So we've already talked about those a little bit. We've already talked about this a little bit too, but it's going to be more important now. So let's take another step back and remember what we talked about before. Remember the exclusion principle that says that 2 electrons cannot occupy the same quantum state at the same time. And so what happens is, what does that mean? It means as you try to squeeze more and more of these electrons together, those electrons have to move to higher energy states. What does that mean? It means they're moving faster. Higher energy means more kinetic energy, which means they have to be moving faster. So the more that you squeeze them into a very small space, the faster those electrons must have to move just to satisfy the quantum mechanics rules. And so, interestingly, as a white dwarf's mass approaches this fundamental limit, 1.4 solar masses, its electrons must be moving so fast that above 1.4 solar masses, you can't actually add any electrons to the mix, because the next one that you add to the mix will be moving faster than the speed of light. And that cannot happen. That is a fundamental speed limit of the universe. Nothing can go faster than the speed of light. And so there is a limit, a 1.4 solar masses, beyond which you cannot support anything by electron degeneracy pressure. And we call it the Chandrasekhar limit. After this astrophysicist, Subrahman Chandrasekhar, an Indian astrophysicist, probably the most brilliant theoretical astrophysicist of the last century, who derived this limit from scratch on pencil and paper. It was pretty amazing. Interestingly, the other way to think about this is, again, as you add more and more mass to a white dwarf, it gets smaller and smaller. 1.3 solar mass white dwarf is already pretty small. If you try to make a 1.4 solar mass white dwarf, it actually gets so small that it disappears. And so that's the other way to think about how this works. If you try to put too much mass into these white dwarfs, this electron degeneracy pressure doesn't work anymore, because these things basically shrink down to nothing. Okay. So we've talked about supernovae. Supernovae are these massive, very bright, very luminous things that happen at the end of a high mass star's life. Now we're moving on from white dwarfs and thinking about high mass stars, because we'd already really talked about white dwarfs. So a type 2 supernova is the type of supernova that we've talked about before. This is the massive star at the end of its life. You reach iron in the core exceeds the Chandrasekhar mass limit, it collapses, the entire star explodes from the inside out. This is a type 2 supernova. And as you can probably imagine, the more mass of the star, the more luminous the supernova. In other words, if you have a 10 solar mass star and it goes supernova, the core collapses, you've got a really bright supernova. If you've got a 20 solar mass star, though, there's a lot more energy there, there's a lot more mass to be blown out, you get a more luminous supernova. So the more mass of the star you have, the more luminous the supernova is, and they can have a range of luminosities depending on how massive the star is that is actually going supernova. There's another type of supernova that I want to talk about that's very important, where that isn't necessarily the case. So let's talk about the type, specifically a type 1A supernova. We're not going to talk about 1B or 1C. So you can just think of these, if you like, as type 1 and type 2 supernova. The type 1 supernova, the progenitor is not a massive star at the end of its life. It turns out you can have a supernova that happens in different ways than that. The progenitor for a type 1 supernova is a white dwarf. So recall the Chandrasekhar mass limit. You don't have to think too far back to remember the Chandrasekhar mass limit. We just talked about it 2 slides ago. But there's a 1.4 solar mass star. So this begs the question. If you make a white dwarf in the normal ways that you make a white dwarf, a low mass star at the end of its life, and let's say that that white dwarf is very close to the Chandrasekhar mass limit. Let's say it's 1.39 solar masses or something like that. Well, it's going to be very small and extraordinarily dense, and it's going to be very close to the limit of collapsing into a whatever happens, exceeding the limit on which it can actually support itself. Now, let's add a scenario to this where this white dwarf is in a close binary system. Let's say it's orbiting another star, and those 2 stars are going around one another. And let's say, so this one, let's say, has gone through all of its stellar evolution cycles as a low mass star. It has gone planetary nebula. It has done all the things. It's become a white dwarf. This one is a lower mass star, and it then leaves the main sequence. What happens? It's going to get much larger. The outer part of this star actually can get so large that it can start dumping mass onto the surface of the white dwarf. Let me show you a little bit about how that would look. Here's our whiteboard. So I'm going to show you, let's say here is our white dwarf. I'll do that in blue. Here is our, oh, I'll do this in red because it's going to become a red giant. How about that? Here is our, here's our normal star over here. And these 2 are going around each other. Imagine that they're orbiting like this, sort of in the plane of the camera. Although it doesn't matter, they could be orbiting like this. Let's make them orbit like this, why not? But this is sort of a snapshot. Now, this lower mass star, even though it's larger, is going to start becoming a red giant. And when it does, it's going to get huge, right? It's going to get gigantic. It's going to get larger in size. I'm drawing this badly, I apologize. Eventually, it's going to get very large. And it's going to get so large that it's going to overflow the region around itself where these are called Roche lobes. And these aren't real things. They are just gravitationally, the regions around each of these massive objects, where if you were to release a particle, it would fall in that direction. Release a particle here, it would fall in this direction. Release a particle out here, there's no telling which way it's going to go. It's going to be caught up in the weird orbital binary. Anyway, what happens when a star expands is it fills its Roche lobe, and it becomes non-spherical. And if it fills its entire Roche lobe, again, this region is stretched out because it's attracted to this very massive object over here. If it fills this entire region, it can overflow. And when it overflows, this region right here is more gravitationally bound to this object than this object. And that material can actually flow onto the surface of the white dwarf over here and collect. So that's fine. And interesting things happen, and you can read about it. That can build up, and you can have surface explosions on the surface of the white dwarf with nuclear fusion happening. We call those novae, classical novae, as opposed to supernovae. But if this white dwarf happens to be at about 1.4 solar masses or very close to it, and then you add some more mass to it, it's possible that that new mass can make this star exceed the Chandrasekhar mass limit. And if that happens, then bad things happen. Okay, basically, you've exceeded the Chandrasekhar mass limit. The entire, what bad thing is going to happen? The entire white dwarf is going to explode. And you get an event that is as bright, if not brighter, than a supernova that we've talked about before. So we call these things supernovae also. It's called the type 1 supernova instead of a type 2 supernova. And these things are extraordinarily important. And we'll talk about why they are important in the next video. So stay tuned.